Continuing on with class 8, here are some more examples. These are out of Cengel, and we have an isothermal process. If you recall the previous Cengel ones, we had an isometric and an isobaric. Now we have an isothermal compression process going on here. So a piston and cylinder device initially are 0.4 cubic meters of air, and they're at pretty much atmospheric pressure and 80 degrees Celsius, which is kind of hot. The air is now compressed to 0.1, so went from 0.4 to 0.1, in such a way, so this is an important little thing, so these are like some magical way that the temperature inside the cylinder remains constant, right? So if you put a thermometer in there somehow and you just compressed it in just the right way, well, you kept your big eye on that thermometer the whole time and said, oh, I'm going to keep that temperature exactly, right? So this is like a pretend scenario, but these are idealized type things, right? So I just skipped something somewhere. Okay, must have skipped that. Okay, excuse me. Well, they actually left a message to the people that were calling before. That's weird. And this is air, so that's kind of important. Anyway, so the V1 was 0.4 cubic meters, and pressure 1 was 100 kilopascals, and the temperature was equal to 80 degrees Celsius, which is also going to, that's 1 equal T2, and volume 2 was going to be equal to 0.1 cubic meters. And just good practice, PV equals MRT. It's a closed system. Nothing can enter unless the mass is the same. We treat it like R is the same, and we're told that this is the same. So these are all constant. Therefore, PV is constant. And N is equal to 1. That's like the polytropic exponent. Polytropic exponent is equal to 1. So we know we can go and take this right here from 1 to 2, and it's going to be equal to P1 V1 times the natural log of V2 over V1. Well, how do you know that? Well, we were told in this equation right here in the book that it was that way, right? For the when n is equal to 1. It's a special case. We can also look it up on what I provided right in here, polytropic process. Was that true? I think it's gonna make a liar out of me. You gotta be careful in here. Yeah, I don't know what you're supposed to do. No, I guess you go to there you go. Constant temperature work is this is not going well. Right here. There you go. That's the right one. See, we know this, we know that, and this. Yeah, we can find it. All right, so we're golden. But you could also, and I have a copy somewhere of no, right there. Let me pause. I'll be right back. Okay, so I'm going to cheat here. This is from Dr. Yevistrick's notes that he shared with me. And information that was kind of interesting. This in a polytropic process, we have N is equal to 1.6 for monotonic gases like helium and argon, 1.4 diatonic gases like oxygen and nitrogen, tritonic gases like, I guess this is going to be I'm not quite sure. I guess this is ozone, right? O3 and SO3. Is that sulfate? I don't know. I don't know I don't remember those things. No, there's just SO2. Okay. Oh, that makes sense. All right. Yeah, the three. That means they have three different things in there. So, sulfate. Is that right? To make sulfuric acid out of. Anyway, he shows that like if we have that set of circumstances, but he doesn't have the other one. So let me fix this. Anyway, he just went through and showed how you could do the integral and set it to a constant right here and plug it back into there, and that you could get your ends to work out. But you could do the same thing. Oh yeah, that's right. You could do the same thing with if n was equal to 1. And that's where you would get the natural log. Yeah, okay. So I don't need to go through that. No, I'm going to do it. I'm not going to be lazy. It's written in a book. So here, let me show you the book. All right, so instead of getting the equation out of looking the equation up, you could also just derive it yourself. PV equals MRT for a constant temperature system. So you just have pressure is equal to a constant divided by volume. So substituting in the pressure right there, you can see that you have dV over V, which you know is a natural log, and you already had what the constant was equal to, was PV was equal to a constant. So now you have the equation as you would expect. All right. So I thought it was important to not just write down this equation, but to see where it came from. It just wasn't on the top of my head of where that came from. So the pressure was 100,000 Newton meters times the original volume, which is cubic meters of 0.4. And then we take the natural log of 0.1 divided by 0.4. And so the important thing to note here is that you get a negative value. And this is Newton meters, or negative 55.45 kilojoules. So what that negative means is that you've added work into the system, and but going between states 1 and 2. So that, in terms of our energy equation, is something, if you recall back in class number 7, we had a sign convention. For heat in is positive, heat out is negative, but work out is usually considered positive, but we have a negative sign in front of there. So it's, in order to get the thing to work out correctly, we treat this as negative because it's adding in, but we're going to have a negative. So if you recall, we had a lot of different things, but basically it was going to like U2 minus U1 is equal to Q 1 to 2 minus work 1 to 2, right? So that minus is built in right there. But if you were adding adding work into the system, then you go to negative right here. So it would be negative, and it would end up having a positive increase in your internal energy. So I just don't want to make another video, so I'm going to do the other example here as well. We're only 9 minutes into this. All right, so we have, so I wanted to do this out by integration, but the example in the book doesn't do it by integration, and I'm not going to be torture myself more than I have to. So we have a spring. There's a spring constant. If you're familiar with the spring constants, you know that force is equal to this spring constant times the displacement, right? I'm just writing stuff down because I'm tired. Kilonewtons per meter. And they say, okay, so the piston starts out with 0.05 cubic meters of a gas, doesn't even say what it is, initially at 200 kilopascals. At this state, a linear spring, this spring right here, is which is touching the piston but exerting no force, right? Now heat is transferred to the gas, causing the piston to rise. So going up right there, heat has been added to it. And compressing the spring until the volume inside the cylinder doubles. right? So V2 is equal to 2 times V1. Therefore, it's going to be 0.1. I can do that in my head, right? Start out with 0.5. If the cross-sectional area, right here, is 0.25 square meters, determine A, the final pressure inside the cylinder, B, the total work done by the gas, and then the fraction of this work against work done against the spring to compress it, which we would call potential energy, by the way, in dynamics. We would consider that. It is a type of work, I suppose, but it is a, we usually designate it as being a particular kind of work, which is potential energy. And so let's see, what other things did we say? P1 was equal to 200 kilopascals, but we don't know what P2 is going to be. Is that true? Oh, we can figure it out. Okay, so what we would do is do an FBD of this. First off, we figure out what the displacement is, how much of a displacement. And I'm going to go keep using X, even though it doesn't make any sense. I should use Y. But recognize that like any change in volume that you might have, you could divide it by the area, and that would be the, amount of movement, delta X, that this thing would make as it goes upwards. And so we had 0.05, that's the change, right? Because we started out with V1 was equal to 0.05, and then we ended with 0.1, so obviously the change is 0.05, and the area we were told is 0.25. So it's going to move 0.2 meters. That allows us to know how much spring force. Here's how much the spring is going to be K times delta X, or 150,000 newtons per meter times 0.2 meters. And we end up with 30,000 newtons. Now, if we want to find out what the pressure is, we could just do this right here. Let's do a free body diagram. We have a spring force, and we have this P that's got placed on here. Well, let's see. We'll have. I don't like how I'm doing this. Let me think about this. Let's go P2, which is going to be P2 times area. Right? It's going to balance out right here. So, but before the spring did anything, let's see. I'm also going to have P1. I don't like that. No. I don't think the free body diagram approach on this is going to help. It's I don't want to get the signs mixed up. I know that P2 is going to be the original P plus the force due to the spring divided by the area. I don't have to write area, just A. Now, how do I know that? This was enough to keep this thing in place before. And so as it started to increase, it got balanced by this force right there, which is now a spring. Times the area. I think that's how I would say it. All right. So we're going to go 320. Where the hell did that go from? No, 200. Sorry. Yeah. Start out with 200 pascals. So 200 pascals plus my 30,000 divided by 0.25. And what we end up with is 320,000. That's where that number came from. Newtons per meter squared, or 320 kilopascals, if you cared about that. And that would be like the answer to part A. I'm trying to think if there's any way that I would have described that better. I think I could have. All right, so now this next part, I decided not to go ahead and attempt to write out a function. We could try to do that, right, and describe how pressure varies with position, because we could say that dv was equal to the area, which doesn't change, times dx, which is the vertical motion right in there. And we could say, well, how does pressure vary with that? We could try to write an equation for it. And I started messing around with it and decided it was just too much. But we could also know that that's going to be equal to the area under the PV curve. I don't know why I write P versus V. See, that's what I'm going to change that. And we can see that we have two different sets right there. We have the one that's due to the change in volume, but we also have due to the change in spring. We can also just look at it, and forget about the fact that it has two parts to it, and say that, well, it has. I'm trying to think what I'm saying here. Okay, it's going to have, it's a trapezoid, right? So we go trapezoid, and in that area, and yeah, either way that you want to approach it, we could go to a trapezoid, or we go to triangle. So let's go to area 1 plus area 2. And so area 1 is just going to be our 200,000 times our change in volume, which is 0.1 minus, 0.05. And those keeping track is 10,000. And we're going to add in. Now what we need to do is take a look at what this height is, and this base, and take 1/2 of it. So you go 1/2. The height is going to be 320,000 minus 200,000. And of course, I didn't really squeeze it in. And squeeze it right into there. So I'm going to go down to the line. Times 0.1 minus 0.05. And all of that is going to be 3,000. So that sort of answers the question. Let's see, first we'll write this down, 1 to 2. It's going to be 13,000 Newton meters, which is 13 kilojoules. So that's answer to part B. Part C is going to be just this 3,000. So the spring, that's the spring potential energy, because that's the area underneath here, because we've made the thing linearly go up here, and there's a relationship between force and displacement. It's been going up that way right there. So we have spring was 3 kilojoules. And I'm tired, and I don't know if anyone's going to bother watching this, but it's just sort of interesting to see that it's the fraction of the work done against the spring to compress it. Yeah, I think I'd buy that. If it was just a spring by itself, that would be the area underneath the thing. Because one thing to remember is the pressure is force over area, and the volume is area times distance right there, distance displaced. So there's both has an area relationship in there. So if you got rid of area, you would be you would still have the same type of relationship in the force through distance. I think that's the right way to say it. Good night. Good night, Irene.